we are discussing different phases in software development. Let us begin by summarizing what we discussed in the previous lecture. We studied the problem definition phase, with which we generally start our development life cycle, where we try to state the problem clearly, try to characterize it, and give a scope of effort and time to the user. The next step we discussed was the feasibility step, where we give different alternatives to the user. We work out their cost and benefits, which may include both the tangible benefits as well as the intangible benefits. And then we started discussing the important phase of requirements analysis, where we specify inputs, processing and outputs. Primarily, we said that the requirement analysis phase goes outside in, where we start by looking at different outputs that the system has to provide to the users, or different types of interactions that the system has to support for the users. Starting from the outside boundary of the software, we work towards the inside and try to identify the inputs and the processing which is necessary to meet the functions of the system. We said that the requirement analysis phase consists of meeting users, finding out detailed requirements as they see them, and in fact maybe also study the existing systems by following the various activities which happen in the real world. Since this activity is a fairly long drawn activity, many people are involved, lot of record keeping has to be done. It's important that we use appropriate tools and also build different types of models through which our understanding can be concisely stated and can be verified with the users. So these are the different phases we have discussed last time. Let us continue further and see what is available further in requirement analysis phase, and what kind of documentation standards are prescribed for recording the findings during the analysis phase. Now, structured analysis has often been accepted as one of the common technique to use during requirements analysis. It consists of focusing on various functions and processes existing in the user environment, and then identifying the data flowing between these functions. We generally use the top-down decomposition approach in this, where initially the whole application is seen as a single process. For this process, we identify the different inputs, outputs, who are the users of the system, what kind of data is stored and which need to be used and which needs to be made available to the application. So at the single process view of the application, the external interfaces in terms of inputs, outputs and users and possible data sources are identified. This is the initial step or the first step. Hereafter, we decompose this process into sub-processes, and we identify the different data which flow between them. The two techniques which we commonly used in the structured analysis method are the function decomposition technique and the data flow diagrams. We will study them in more details subsequently, but basically the idea here in the functional decomposition is that the overall functionality of the software system we plan to develop is broken down into subtasks. For example, in a railway reservation system, we may have one sub-function called reservation, the next one called cancellation, the third which may consist of producing various types of reports, and the fourth could be maintaining the data about various trains and schedules and timetables and so on. So we decompose the overall functionality into subtasks or sub-processes. This is the function decomposition. And once the function decomposition has been done and the sub-processes have been identified, we also can establish what kind of data flow takes place among these sub-processes. So, this is the methodology in the case of structured techniques, and subsequent to doing this kind of analysis where we start from a single process view and decompose it, we proceed further to establish what is called the current physical data flow diagram. So, we start by studying the existing system, we understand the sub processes, we try to find out what is done and where and how it is being done. So, the beginning point is the existing system. From here, the data flow diagram that we produce naturally corresponds to the current system, and it corresponds to the physical view of what is happening in the real world. So, we call it physical current data flow diagram. From here, we prepare a logical data flow diagram by removing the current implementation specific details. Basically, we want to now focus on the what specification, what exactly is done or what is required to be done rather than how it is being done. So, we try to construct the logical data flow diagram from the physical current data flow diagram. We then also identify the boundary of automation. What is the scope for the software system? Which processes and sub processes would be included in the scope of the software? Once this is done, then we prepare the data flow diagram for the proposed system. In fact, the difference between the existing system and proposed system has to be clearly worked out, and this would depend on not only the user's requirements, but it would benefit from the experience of the analyst, the innovations that he can suggest in the existing processes, so that the proposed system will effectively solve the problems which were felt by the user and which has initiated this whole project. So, the proposed system is not just a duplication of the existing system. We are not only changing the way the things are done today, but we may even extend the scope of the system. We may suggest new tasks, new functions, new outputs from the system. So, this would depend on the vision and the experience of both the users in terms of what they need in order to solve their business problems effectively, and the experience and vision of the developer or the analyst who is assisting the user in identifying the requirements. So, naturally this will include new needs of the users. The proposed system would improve the workflows. It might do some business process re-engineering. It will try to introduce efficiency and more effectiveness in the way things are done at present. So, idea is to prepare the data flow diagram for the proposed system. This proposed system will become the basis for software implementation subsequently, and once this proposed system is clearly defined in terms of its inputs, processing, outputs, then we are ready to develop or to prepare the documentation for this particular phase, which results in the preparation of what is called the software requirements specification document. We will now look at the format of the requirement specification document. It is very important to understand this clearly, because this is one of the very important document. As we said earlier, it becomes a baseline for a contract between the user and the developer. It is expected to contain the complete requirements which are adequate to tell the user what he would get from the software, and it is also adequate to tell the designers and developers subsequently for the complete implementation of the software solution. So, let us understand the documentation format which has been standardized by IEEE. This is the format that we are discussing, is as per the recommendations given by the IEEE organization, which has made lot of recommendations for software standardization. We will study the different sections which this document will consist of. The first section is the introduction section. It first establishes the purpose of this document. What exactly is the purpose and what is covered in this document? Then it defines the scope of usage. Who will use this document and for what purpose? It gives various definitions, abbreviations, acronyms as they may be applicable and which have been used in the rest of the document. It may also refer to other documents which have been prepared and which have been referred by the user. For example, these may be documents made available by the user which define some parts of his requirements, or these may be documents which were prepared during feasibility step. All these documents can be referred here clearly in the SRS document. Finally, the introduction will also briefly specify the responsibilities of the developer. What exactly is the scope of the project? Does it include development, installation, training, maintenance, support for a limited time, etc. All these responsibilities are also clearly stated briefly in this section. So, introduction section is an overview of the document's purpose and references and the responsibilities. These are clearly stated, and this is the first section of the SRS document. The next section is the general description of the software that we plan to develop. It first contains the product perspective. Here we see the product as a single unit and try to establish its overall context. We see it as a black box. How does it relate to possibly other software products? What are its interfaces with the other products? So, this is taking the perspective about the product in its overall context, what exactly its relationships are with other products. Then it defines or it states the functions of the product briefly. These are the general overview of various tasks that the product is supposed to perform, including references to data flow diagrams. This product function overview is as the name suggests, is an overview of the functionality of the software. We then try to characterize the users for whom the software is being developed, and we also mention the different constraints which are placed. These constraints may be about the schedule of development, the resources such as existing system and software packages, constraints about the cost and other resources. So, the section 2 of the SRS document is a general description giving not only the overview of the product's features, but also placing it in proper context in terms of other products, in terms of users who will use, what characteristics we can assign to these users in terms of their expertise and training and so on. So, these are the general descriptions which are covered in section 2. Section 3 is really the core part of the document. In this part, we give functional details. We define every function of the software by giving a brief introduction to this function. Then we describe the inputs to the function, processing and the outputs. So, these functions may be different functions that the software will perform. For example, it may be a function related to reserving a seat on a train or cancellation of a ticket already booked. So, these are different functions or tasks. Each of them needs certain inputs, performs some processing and produces some outputs. So, for every such function, we give description in this particular section. So, section 3 is really the body of the SRS document where functions are described in full details. In section 4, we give summary of external interfaces of the software. We first define the user interfaces, that is the human users, what kind of screens or outputs they would receive, what kind of commands they can give, what kind of error messages may be thrown up by the software. In fact, this section of the document can be treated as a preliminary user manual. In fact, it is this section which will give a good idea to the user about the kind of system he is likely to get at the end of the development. We should note here that we are not doing any design. At this point, the user interfaces are specified more in terms of contents. Right? What are the logical contents of different interfaces or different commands that will be made available to the user in order to use the software we are developing. So, we must remember this point, that at this point exact screen formats, screen layouts, report formats are not essential. It is the logical contents of these components which are specified, and in terms of which the user will try to get a good idea of what kind of system is being developed. Then we also describe the different hardware interfaces. Of course, these interfaces are applicable when we are interfacing with specialized hardware for meeting some functionality of the software. For example, this might be a hardware interface to control some chemical process. So, these hardware processes are also clearly specified. Then we have software interface specifications. In case the product that we are developing has to interface with some existing packages, then those interfaces are clearly specified here. For instance, the railway reservation system may interface with the accounting system of the railways, so that all the fund collections are automatically transferred to the accounting system. Now, this accounting system may be already existing. So, our railway reservation system package that we might be developing will have to interface with such an accounting package. So, these software interfaces are also clearly specified. We also define here performance requirements. These performance requirements would be used subsequently for defining the sizing of the various elements of the software or the hardware. So, for example, we will identify the number of users, the volumes of data, the response time requirements, the throughput requirements. These requirements are specified in terms of users requirements. That is, what kind of environment in which the system will function, what kind of workload it will have, what response time is expected from the system. So, if the system is a real time kind of a system where it is processing online transactions, then we need to define the throughput and the response time. Consider the example of, say, banking. When the banking software has to accept transactions from the customers, then we need to identify in how much time the system must react to the input of the transaction, or totally in a particular given time, which may be the peak time, how many transactions should the system process in a given slot, which could be 1 hour or some such thing. So, these are the capacity requirements which are important to be specified, and they are specified from the user's point of view, and these are defined by taking into account what are the actual requirements of the organization. So, after identifying these, we identify the various design constraints. Now, these constraints may be in terms of the development standards. The organization may have very specific standards for developing the software, or it may be standards for various reports. For example, in the financial world, lot of reports are required by regulatory authorities. So, these reports must be as per the standards. Then there are auditing requirements. So, these standards needs to be complied with, and those must be clearly identified, and they are identified in this section. We also identify any hardware limitations. For example, the user may already have some machines, operating systems, database systems, etc., and we may need to develop the software for the available environment. So, these would be treated as hardware constraints or system constraints. And finally, we state any other requirements possibly mention here the future extensions for the software. Now, this is the overall format for the SRS document, which is giving a complete specification of the software in terms of what it would contain. Now, we must note here that all sections which are listed here may not be required in all projects, because some projects may be very small in scope, but in most cases these different sections would be necessary because they cover various aspects, not only the functions, but they cover constraints, they define functional requirements, they define performance requirements. So, one can see here that SRS format has taken into account various aspects, and we can see that by using this specification format, we are meeting our expectation that the document will clearly tell the user what features and functions the software will provide and how he will be able to use it. Similarly, we have made it detailed enough so that from here we can hand over this document to our design team and they will be able to convert the specifications into a design. So, a SRS document, which is a baseline document, needs to be detailed, and we must ensure that we have collected all this data and put it in the form of a document. So, once the SRS is prepared, which can be an extensive task for a large software, we need to review this with users. There has to be a formal review meeting in which the entire SRS document would be reviewed, and there should be a sign off where the users would say that yes, the SRS document clearly defines what the system needs to do, and also there will be some peer review which will ensure that the document contains enough details for the design activity to be carried out. So, we are going to do the design subsequently. It must contain enough details so that the design can be carried out. We can define the platforms, we can define the capacities, we can work out the sizes required for the different systems and so on. All these must be possible from the SRS document, and we see that it is detailed enough to give us all this data. It is very important that the analysis phase results in preparation of such a detailed and standard document. So, we proceed further only when the document is accepted by the users as being complete in all respects. Once it is signed off, we proceed to the next phase, which is the design phase. In the design phase, our objective is to formulate the implementation strategies for the problem that has been identified. So, now we move to the how part of the solution. In the SRS phase, in the requirement analysis phase, we have defined what part of the problem, what is the problem. Now we are trying to address how the problem should be addressed, how it should be solved. Input to this phase is naturally the SRS document from the previous step. We now try to consider different technical alternatives. We must remember that SRS is a logical document. It specifies the requirements without dictating how those requirements must be implemented. Design phase is the first phase in which we make a transition towards the solution. Different alternatives may be available. These are primarily technical alternatives. What kind of technology we should use for solving the problem. Now, after this point, we are going to increase our efforts from phase to phase in order to build the software. It is important to review at this point once again whether the automation boundary that we have defined is the appropriate one or not. So, we look at not only the different types of solutions which may be possible based on the technology options, but we may once again consider the business functions which need to be put into the scope of the system. We also consider what type of solutions to create, whether they would be batch or online type of solution, including whether we should make the software or buy something which is readily available in the market. In fact, these are different alternatives in order to realize the goals which have been stated in the SRS document. So, this is a point at which again we consider different alternatives, and these alternatives may have different costs and different efforts. They may need different time to complete the project. So, it is important to consider these technical alternatives once again, whereas in the feasibility study we did consider various alternatives which were primarily based on business alternatives. Now we explicitly consider additional technical alternatives. Now we are doing it again because we have a very good understanding of requirements now. We have completed the requirements specification. This is appropriate point to consider different technical alternatives. The purpose of coming up with different alternative is to provide user different options which may be starting from low cost options to medium cost to high cost options, naturally giving different cost effectiveness, different benefits to the user in terms of the meeting of overall requirements. For each alternative, we prepare a system specification, we prepare implementation schedule, and if necessary we carry out the cost benefit analysis, because the costs are going to rise significantly from this point onwards. Since we understand the scope better now, we will be able to do a better cost benefit analysis at this point. We then prepare the design document, and which is then reviewed both by technical people as well as the management people. The technical people would review the document to ensure that different technological options considered are meaningful and all important or all applicable options have been covered, whereas the management review would be concerned with identifying whether there are implications on costs, benefits and so on. So, this is done again, and the purpose of the review is to ensure that we are within the proposed costs and we will be able to meet the schedules, and the technical review would ensure that there are no errors in the proposed design, that it is consistent and complete, and various applicable alternatives have been worked out. This phase should end with a clear choice. So, the different alternatives which are prepared in terms of different system designs are reviewed both by the management and the users, and it ends with a clear choice which can then be further taken into detailed design and implementation. What are the design goals in this phase? In this phase, we are trying to define or do a complete do a design of the processing component, because the requirements have clearly defined the different processing needs of the user. So, this processing component will be converted into software. We have a functional approach as well as we have a object oriented approach. So, different alternatives are available for design methodologies. They may be the conventional functional development or it could be object oriented development. There are different methodologies available for the paradigms. So, if it is a functional paradigm, you may use structured system analysis and design methodology, which is based on taking data flow diagrams and converting them into software architecture, taking entity relationship diagrams and converting them into database design. Or it could be an object oriented paradigm and the associated object oriented methodology, in which you convert it into a object oriented implementation. So, the kind of design methodology you choose would depend on the paradigm that you want to employ for implementing the software. If you are designing the functional component separately, you also need to design the data component. The data component generally is handled by designing a database for the given application. A database design consists of multiple steps. For example, the first step is generally the step in which the normalized database design is worked out from the entity relationship model. Now, all database systems have a particular data model, such as the relational database model. We will study this issue in some more detail subsequently, but when we prepare the entity relationship model to understand the information domain of the user, this is a conceptual data model, and this needs to be converted into a database design. After doing a normalized or a conceptual database design, we modify that if necessary for getting good performance from the system. This often is called denormalization. And finally, a step in database design is consisting of choosing the right storage techniques through which data can be accessed efficiently. This might consist of creating different indexes to the data stored in a database. So, in general, the design of a software consists of designing the processing component as well as designing the data component. These two components may be designed separately, or they may merge into a single design dimension when we use object oriented technology. Usually a large complex software will be decomposed into what we may call partitions or layers. We do not implement a large software as a single module or a single routine. It consists of different segments or partitions as shown in the diagram here in front of me. As you see here, the overall software represented by a boundary as a rectangle consists of layers in this case, and these layers have a different functions, and they pass messages or they make calls on features provided by a lower level in order to carry out their tasks. Similarly, you may also decompose the software into partitions where each partition carries out a specific responsibility. So, the overall complex software is built by decomposing it into partitions and layers, and each partition and layer is given a specific responsibility. We define different subsystems at the software level. We also define modules. In fact, modules are the building blocks of the overall software. Each module has a specific function to perform. Module may be a piece of code which, when executed, carries out a specific task. Such modules together may make a subsystem. Multiple subsystems like this will make up the overall system. So, a subsystem may be representing a partition or may be representing a layer. So, this vertical and horizontal decomposition of the overall software is necessary in order to divide it and to break it into realizable components. These modules will naturally make a call on each other. They will pass data and they will collect results. So, module is the building block, and the different modules are interrelated in terms of execution. A module may invoke another module and pass certain data to this module and expect certain computations. For example, a module may sort the data in an ascending order, or it may compute the tax for a given employee. Now, this module expects certain data to be given as input and it produces results. Such a module will be called from another module. So, we are talking now about the execution architecture of a given software, which is defined in terms of modules and the calls that they make on each other. Now, these modules are important elements, as we just now said, that these are the building blocks, and a good software architecture should make these modules as independent as possible. An independent module is one which has a clear responsibility, which has a well defined task to do. It does its function, which is a very cohesive kind of a function. So, modules should be independent, they should have minimum interdependence. These characteristics are important from the maintenance point of view, and this is a basis for handling complex tasks. Complex tasks must be broken into subunits. These subunits must be cohesive, they should have little interference from other modules, there should be minimum interdependencies, so that a module can be replaced by an equivalent module without disturbing the overall functioning, and this replacement may be done for various reasons during the maintenance. We decompose the modules or the subsystems until we reach units which are implementable, which can be coded and tested. The software architecture that we try to define in terms of modules and interrelationships among them can be captured through a notation or a diagramming tool called structure chart. Structure chart is used in functional methodology. It depicts different modules and their calling relationships. There are techniques available to arrive at such a design consisting of modules and calls among them and produce a structure chart. There are techniques available to go from data flow diagram to structure charts. A structure chart basically is a hierarchical chart. The modules can be organized at different levels, so that module at level I calls the module at level I plus 1. A hierarchically structured set of modules have modules organized at different levels, and the control flow is not shown, only the calling relationships is shown. So, here we are putting some kind of a discipline in the software architecture that we are designing, that the architecture will have a hierarchical structure and modules at one level will call modules only at the next level, and there will not be arbitrary calls among the modules. This ensures a systematic architecture for the software, and this is a very important design guideline. Here is a diagram which shows a example of structure chart. As you see here, we have a task 1 which is shown as a module at the top. This task has been written as a software module or a unit. It calls on 3 modules at the next level. These 3 modules have been named as get input, processing and produce output. That the lines which are connecting these modules basically represent the call that the module task 1 makes to get input or processing in order to perform its own job. So, the structure chart basically shows modules as rectangles and links among them representing the call relationships. These modules call each other to perform their own overall tasks. As you see here, the task 1 invokes the get input module. You can see that there is a data item named X which is flowing from get input and going towards task 1. Basically, here what it implies is that the task 1 needs this X and it has given this responsibility to the get input module. So, it calls the get input module and receives from this module the data item X, which it may then pass to the processing module. As you see here, the X data item is traveling from task 1 to processing. The Y data item is actually being produced as a result from the processing, and it is being sent back to the task 1. The task 1 then is passing this Y to the produce result module. So, in general, the modules which call each other may have some data items flowing from the calling module to the called module, or there may be some results which are going back to the calling module. This is the data which flows as parameters between the modules when one module executes or invokes another module. As you see here, again the modules are organized at different levels. So, the task 1 is a module at level 1 and the other 3 modules are at level 2. The module at level 1, that is the task 1, is the one which invokes or which calls the modules at the next level and not the other way around. This is the hierarchical structure that we enforce on the software design. Software design therefore consists of identifying these modules and the hierarchy of the software. This hierarchy represents the architecture of the software. If necessary, the module 2, the modules on the level 2 such as the processing module can be decomposed further. So, the hierarchy can consist of multiple levels depending on the complexity. We can keep decomposing till we arrive at a module which is clearly specified and which can be implemented in terms of a code module which can be converted into a program. The modules at higher level generally do the coordination and control, whereas the modules at lower levels do input, output and computations. This is exactly what we saw in the previous diagram. The module at the higher level, which was the task 1, is the one which gets work done from the modules at the lower level. So, it obtains inputs, it obtains computational results and it passes them from one module to another module. So, the task of coordination and control usually gets done at the modules at the higher level, whereas the modules at the lower level, you can think of them as worker modules. They actually perform the tasks such as the input output tasks and the computational tasks. Structure chart also shows important data, as we just now saw. These data are shown as flowing between the different modules. They may be either data coming into the module or the data going out from the module to the calling module. Usually you do not show the control flow in the structure chart. However, some important control flow or structures such as decision making and iterations may also be shown on a structure chart without giving too many details. In fact, this is only to indicate to the reader of the structure chart that some modules may be repeatedly executed, whereas some modules may be executed only depending on certain condition. So, a few notational extensions are made to the structure chart as shown in the diagram here. The diagram at the top shows iteration. It shows that module A may repeatedly call on modules C and D. The diagram at the bottom has a small diamond here which indicates that module A will call module C or D depending on some condition. In fact, the details of the condition or the details of how often the iteration would be done are not given on the structure chart. It only shows that such a iteration or a decision making is present in the software, and these are the important repetitions or iterations and the important decisions which are made in the software functions. In the object oriented approach, the software consists of different classes. In fact, class is the main concept in the object oriented approach, where it has both the data associated with the class and the executable functions associated with the class. So, we call these as structure and behavior for the class. This is a paradigm which combines the data and the processing together on a single dimension and identifies classes which have structural properties and which have behavior or methods defined for them. It is a completely different paradigm, and we will see more details of this subsequently. Object oriented paradigm is very useful and has occupied a very important position in the design of software, and it simplifies greatly the complex software development. It has not only a new notion of a class as a unit for organizing the processing as well as the structure, but it provides a concept of inheritance which allows us to reuse the software from other existing components. We use class diagrams to show the static structure of the system. The class diagram identifies what are these different class components, and besides the class diagram we use interaction diagram which indicates the dynamic behavior of the system in terms of classes interacting with each other. So, we will see this object oriented approach subsequently in much more details. The only point that we want to make here is that there are different ways in which the design can be approached. It could be the conventional approach where the architecture consists of functional modules depicted in the form of a structure chart, or it could be an object oriented approach. A object oriented approach will decompose also large system into various packages. So, the principles are similar, that you use the decomposition technique into to convert the large software into smaller components. These components may be modules or they may be classes, and we organize the data and processing among these. Once we have completed the design and also have finalized the approach, we can prepare our design document, which also has a well defined structure. The design document will generally include these different sections which will specify the design completely. We start by giving an overall introduction, then we define the problem for which the design has been prepared. If necessary, we indicate here the different diagrams such as data flow diagrams, entity relationship diagrams, or class diagrams which have been prepared by us, and we enclose them as appropriate annexures. Then we define the software structure in terms of the architectural diagrams. We define the data in terms of the various database structures, the files, or any other important data structures. We give the module specifications which indicate what inputs they take, what processing they perform, and what are the subordinate modules which they use. And finally, we do the tracing of requirement. We indicate how these different modules meet the various requirements that have been identified in the SRS document. So, the design document is now a fairly technical document. It consists of our approach towards building the software. We have identified the components which will be implemented as part of the overall software. This document needs to be reviewed by the technical people who will see that the document is detailed, it is comprehensive, it is complete, and also that it can be traced and can be mapped to the SRS document. We ensure through this requirement tracing that the design document covers all the functions which were identified in the SRS document. After doing the overall design or the high level design, we perform the detailed design. In the detailed design, we now go towards details of making these modules implementable. We give now the inputs which have been prepared from the previous design document are made available, which consists of software architecture, the different modules and the different database and file design. In this detailed design step, now each component will be further refined so that we make it ready for implementation. Here the deliverables will include detailed program specification, where we will indicate the logic or the algorithm for different modules. We will give the file and the database design. We will give the hardware specifications if they are applicable. We will make detailed test plans, and also we will give the implementation schedule. So these are the deliverables of the detailed design, and the input to the detailed design is the design document which comes from the first high level design step. This detailed design document will be prepared giving all these specifications, and it will end in a technical review. Technical review at this point will consist of walking through the different specifications and ensuring that the specifications are complete for us to begin implementation. We go to the implementation phase, which naturally consists of coding the programs, testing them, documenting them. After the soft code has been prepared, we also have the responsibility of converting the existing data which may be in a manual system and creating initial file and database. We prepare the operating procedures for the users. We do the overall system testing, where not only individual modules are tested but the whole system is tested. Then we carry out the user acceptance, where the user will do a functional walkthrough for the system that we are ready to deliver to him. So functionally it should be acceptable to the user. Moreover, it should also be acceptable in terms of performance. Remember that in the SRS document, the performance criteria were also specified. So at this point, the SRS document will be used by the user to carry out the final acceptance of the system. Once the user has accepted the system, we are ready to switch over, the system can be installed. And once the system is installed, we are ready to use the software in day-to-day operations. So this then is the next phase, which is the operations and maintenance phase. In this phase, we ensure that the system will continue to meet the user needs. And in order to do this, we may have to take up maintenance activities. The maintenance activities consist of removing any errors that the users may find in the software, or extending the present features in the software for new requirements that the user may have. So we might make some extensions, or we may even add entirely new features. Occasionally it may also be necessary to convert the software to run on new platforms or new systems, because the software might have a fairly long life, and during this time the hardware or the systems may change significantly, and we may want to change the platform of the software. So these are the maintenance activities, and these generally continue throughout the lifetime. Let us summarize the study of various phases that we have carried out. We have seen that there are different phases, and each phase has a well-defined task and has a well-defined deliverable. In many cases, these deliverables have a standard format. We have seen that feasibility was one of the very important steps. It establishes different alternatives, and these alternatives are analyzed for the cost effectiveness. Requirement analysis is a very important step and also very challenging, where the analyst or the developer has to prepare the complete specifications for the software by meeting the users, by going through the existing system if necessary. So this is going to be the first baseline, and we saw that there is a IEEE format which is very comprehensive and which defines the various aspects of the software which needs to be developed. Then we saw the design step. The design step consists of designing the architecture of the software, also designing the databases, and naturally it will also consist of designing the various interfaces that the users have with the software. Now, in the rest of the course on software engineering, we will take you through some of the details of these design techniques. Similarly, we will take you through the details of some of the modeling techniques. In this particular lecture, we have only given a broad summary of different phases through which the different steps are carried out, the different phases of the life cycle. And we saw that each phase ends in a technical or management review.